Right now, sitting in a locked titanium tube on the floor of an ancient Martian lake, there may be the most important rock sample in scientific history waiting for us to come pick it up. Subscribe, there's a new one every few days. This is White Space. Settle in, for as long as human beings have looked up at the night sky, one star has looked back at them differently from the others. It doesn't twinkle the way stars do, it holds its light steady, a fixed burning point that moves slowly across the constellations over weeks and months, wandering against the fixed background of the sky. And its color is unlike anything else up there. Red. Not the red of a fire or a sunset, but a deep, mineral red, the red of dry earth, the red of iron left in the rain. Cultures on every inhabited continent noticed it and built mythologies around it. The Babylonians called it Nergal, god of death and plague. The Romans named it after the god of war. In Chinese tradition, it was Yinghuo, the fire star and omen of calamity. The Egyptians called it Herdesher, the red one. Every civilization that watched the sky carefully enough to notice its movement gave it a name, and almost every name carried weight, significance, foreboding. The ancient dread was not irrational. Mars is genuinely strange to the naked eye. Unlike the other planets visible without a telescope, it moves in a way that seemed inexplicable for centuries. Most of the time, it drifts eastward against the background stars. But periodically it slows, stops, reverses direction, moving west for weeks or months before stopping again and resuming its eastward drift. This retrograde motion, as astronomers call it, puzzled thinkers for 2000 years. Ptolemy's geocentric model of the solar system required increasingly elaborate constructions of circles within circles, epicycles, to account for it. The motion made Mars a puzzle, a source of mathematical frustration for anyone who tried to reduce the sky to predictable geometry. It was Mars that finally broke the geocentric model. In the late 16th century, the Danish astronomer Tycho Brahe compiled the most precise naked eye observations of the planets ever assembled. Measurements of position accurate to about 1 arc-minute, an extraordinary achievement before the telescope. Brahe died before he could finish analyzing them. His assistant, Johannes Kepler, inherited the data and spent years trying to fit the motion of Mars to a circular orbit around the Sun. The Copernican model that had replaced Earth with the Sun at the center, but retained the ancient assumption that planets move in perfect circles. It didn't work. Mars kept deviating from where a circular orbit predicted it should be by small amounts but consistently. After years of calculation, Kepler tried an ellipse and everything fit. Mars gave astronomy its first law of planetary motion. Orbits are ellipses, not circles. Every space mission ever flown has been planned using equations derived ultimately from Tycho Brahe's patient measurements of one red star. The telescope revealed what the naked eye could not. In 1659, the Dutch astronomer Christian Huygens made the first drawing of a surface feature on Mars, a dark triangular region we now call Syrtis Major, and used it to measure the Martian day. He found it was almost exactly the same length as an Earth day, 24 hours and 37 minutes. This coincidence astonished and delighted early astronomers, and it deepened the intuition that Mars might be a world not entirely unlike our own. Giovanni Cassini, observing at around the same time, was the first to notice the polar ice caps, white regions at the north and south poles that grew in winter and shrank in summer. Seasonal ice caps. Another parallel to Earth. Another reason to believe that Mars might be hospitable. The 19th century took this intuition to an extreme. In 1877, the Italian astronomer Giovanni Schiaparelli observed Mars during a particularly close approach and produced a detailed map of its surface features. He named the dark regions and described linear features connecting them, which he called canali, the Italian word meaning channels, appropriate for any elongated natural feature. When his work was translated into English, canali became canals. A canal is not a channel. A canal is built. The confusion would shape popular understanding of Mars for half a century. The American astronomer Percival Lowell seized on Schiaparelli's canals and constructed an elaborate theory around them. Lowell, a wealthy Bostonian who built his own observatory in Flagstaff, Arizona, spent years mapping what he believed was a global irrigation network built by a dying civilization to transport water from the polar ice caps to the equatorial deserts. He published 3 books on the subject, wrote extensively for popular audiences, and attracted enormous public attention. The Mars of Lowell's imagination was a world in its final chapter. An ancient civilization facing ecological collapse, brilliant engineers desperately redistributing their planet's last water resources. H.G. Wells read Lowell and wrote The War of the World of the Worlds. Edgar Rice Burroughs read Lowell and wrote John Carter of Mars. The canals of Lowell were fictional from the beginning, artifacts of human pattern recognition, straining against the limits of available optics, but they fired an imagination that persists to this day. The canals died slowly. Better telescopes, better observers, and eventually the consensus of the scientific community concluded that Lowell's linear features were not real, that they were an artifact of the visual cortex's tendency to connect isolated dark patches into continuous lines when the details are just below the threshold of resolution. But Mars retained its grip on the human mind even as the canals faded. And when the space age arrived, Mars was always the first destination after the Moon. The first spacecraft to reach Mars successfully was Mariner 4, launched by NASA in November 1964 and arriving at Mars in July 1965 after a journey of 228 days. It did not land, it flew past, taking 22 photographs through a narrow-angle television camera during a close approach that lasted about 25 minutes. Those 22 photographs were the first close-up images of another planet ever taken, and they contained almost no good news for the people who had grown up imagining Mars as a second Earth. The images showed a cratered, desolate surface, not the irrigated landscape of Lowell's imagination, not the eroded terrain of an ancient river system, but a scarred, airless-looking world that resembled the Moon more than anything else. The atmosphere, measured by a radio occultation experiment as the spacecraft passed behind Mars, turned out to be far thinner than anyone had hoped. The surface pressure was perhaps 1% of Earth's, not the thin but breathable air some scientists had still clung to, but a near vacuum hostile to life as we understand it. Mariner 4 was a blow to optimism, but it photographed only about 1% of Mars's total surface, and that 1% happened to be among the most heavily cratered, geologically ancient terrain on the planet, not representative of Mars as a whole. 6 years later, Mariner 9 arrived in November 1971 and became the first spacecraft to orbit another planet. It arrived during the most intense global dust storm on record, and for weeks, the planet below was completely invisible, its entire surface shrouded in an opaque reddish haze. Engineers had no choice but to wait. They pointed the cameras at the Martian moons and took photographs while they waited for the planet to reveal itself. When the dust finally settled, starting from the top down as the upper atmosphere cleared first, the revelation was gradual and astonishing. The first surface features to emerge from the haze were 4 dark spots arranged in a rough line near the equator. For days, no one was certain what they were. They appeared elevated above the dust layer, as if standing above whatever had obscured everything else. When the resolution improved enough to show their structure, the answer became clear. They were the summits of volcanoes. And the tallest of them, the one that had been visible as a smudge through Earth-based telescopes and catalogued under the name Nix Olympica, the snows of Olympus, was not just a large volcano, it was the largest volcano ever identified anywhere in the solar system. As the dust continued to settle, the extent of the Tharsis Plateau emerged, an elevated region roughly the size of North America, dominated by the line of enormous shield volcanoes that had left their summits protruding above the dust cloud. Then, running east from Tharsis, a rift system appeared that dwarfed anything on Earth. Valles Marineris, named in honor of the spacecraft that revealed it, extended for thousands of kilometers across the planet, a scar on the face of Mars so large that the first engineers to see it in full simply could not initially accept the scale their instruments implied. Then the ancient terrains appeared. The southern hemisphere of Mars, as it emerged from the haze, was heavily cratered, an ancient battered surface that looked much like what Mariner 4 had shown, but cutting through it were branching valley networks that bore no resemblance to anything formed by simple impact or volcanic processes. They were the desiccated remnants of drainage systems, ancient river channels and their tributaries, carved into rock billions of years old. They could only have been made by running water. Running water required a warmer atmosphere. A warmer ancient atmosphere meant Mars had been a radically different planet at some point in its past. Mariner 9 mapped 70% of the Martian surface at resolutions between 1 and 3 kilometers per pixel, transformed every existing model of the planet, and set the research agenda for the following 50 years. Every mission that has gone to Mars since, every lander, every rover, every orbital radar survey has been answering questions that Mariner 9 first made it possible to ask. On the 20th of July, 1976, a signal crossed the void between two worlds. It had been traveling for 19 minutes the time it takes light to cover the distance from Mars to Earth. When it arrived, engineers at the Jet Propulsion Laboratory in Pasadena gathered around their receivers, and for a moment the room went quiet. Viking 1 had landed for the first time in history. A machine built by human hands had successfully set down on the surface of Mars and was still alive, still transmitting. The first image came through line by line, assembling itself on a screen in strips of gray. It showed rocks, reddish angular rocks lying on a flat, rust-colored plain, nothing alive, nothing moving, just stone and dust and an ochre sky, and yet the room erupted. Because those rocks were sitting on another planet, and the camera that photographed them had been made by people who had never left Earth. Viking 1 had been in transit for nearly 11 months. Its journey began in August 1975 from Cape Canaveral, launched by a Titan toy rocket powerful enough to hurl a spacecraft weighing nearly 3,500 kilograms onto an interplanetary trajectory. The craft consisted of an orbiter and a lander. After 11 months of travel, it entered Mars orbit, and for the next month the orbiter circled the planet at high altitude, its cameras scanning the terrain below in search of a safe landing site. The original target had looked promising in older photographs. Up close, it was a chaos of boulders and craters. Mission controllers selected a new location. Chris Planitia, the Golden Plain, a broad sedimentary basin near the mouth of ancient river channels that had not carried water for perhaps 1 billion years. The lander separated from the orbiter and fell. It hit the upper atmosphere at more than 16,000 kilometers per hour. An aeroshell slowed it from the outside. A parachute opened at an altitude of about 6 kilometers. Then, at 1,200 meters above the ground, the parachute was cut away and 3 landing legs extended, while 12 small hydrazine rocket engines ignited, slowing the descent to a gentle 2 meters per second. Contact, a single switch tripped as each footpad touched the ground. All 3 switches tripped within fractions of a second of each other. The lander was stable. It was alive. Over the months that followed, Viking 1 analyzed the Martian soil with instruments no scientist had ever used on another planet. It sampled the atmosphere and confirmed it to be 95% carbon dioxide with small amounts of nitrogen, argon, and oxygen. The atmospheric pressure at the surface measured about 800 pascals, roughly the pressure a person would experience at 40 kilometers above Earth, far above the stratosphere, above even most weather. The soil samples were fed into a miniature biology laboratory, a self-contained chemical factory occupying a volume smaller than a household appliance. It ran 3 separate experiments, each designed to detect a different kind of biological activity. The labeled release experiment moistened Martian soil with a nutrient broth containing radioactive carbon atoms. If living organisms consumed the broth and respired, they would release radioactive carbon dioxide. Something did release gas, and the initial result caused brief, intense excitement. But further tests showed that the reaction stopped when the soil was heated to temperatures that destroy biology, but not chemistry. The most likely explanation was an inorganic oxidizing agent, a chemical, not a microbe. The gas exchange experiment found anomalous oxygen release consistent with chemistry, not biology. The pyrolytic release experiment showed ambiguous, very slight positive results. The definitive blow came from the organic analysis instrument, a gas chromatograph mass spectrometer powerful enough to detect organic compounds at parts per billion. It found none, no amino acids, no lipids, no complex organic molecules of any kind. Biologists know of no life that fails to produce detectable organic compounds. The consensus that emerged from years of debate was that the Viking results reflected unusual hyperreactive inorganic chemistry, likely driven by perchlorates and superoxides in the Martian surface soil rather than biology. Mars in 1976 appeared to be lifeless. Viking 1 did not find life, but it found Mars, its chemistry, its seasons, its winds, the thin frost of carbon dioxide that formed on rocks in the Martian winter. It transmitted data for more than 6 years before its computer was accidentally overwritten, and the signal went silent forever. Viking 2 landed on the opposite side of the planet in Utopia Planitia, 45 days later, and conducted the same experiments with the same results. Together, the 2 landers gave the first systematic portrait of Mars from the ground. A cold, chemically reactive desert, almost certainly barren at the surface, and almost certainly so for a very long time. For more than 2 decades after Viking, Mars remained largely quiet from the perspective of active exploration, a gap filled by theoretical work, by continued analysis of Viking data, and by the slow development of the spacecraft that would follow. Then, in the summer of 1997, everything accelerated. Mars Pathfinder arrived on July 4, 1997, bouncing to a stop on the Martian surface inside a cocoon of airbags, a landing system radically different from Viking's rocket-braked legs and far cheaper to engineer. The entry, descent, and landing took less than 4 minutes from the top of the atmosphere to the ground. In those 4 minutes, the spacecraft went from 27,000 kilometers per hour to 0. The airbag system, tested against every conceivable failure mode in the deserts of California, worked flawlessly. The landing site was Aris Vallis, a floodplain at the end of one of the great ancient outflow channels of the Tharsis region, where a catastrophic flood had once swept rocks from a vast upstream catchment area and deposited them randomly across the plain. A lander here would encounter a geologically varied sample without the rover needing to drive far. The choice was methodologically elegant. The lander was named the Carl Sagan Memorial Station after the astronomer and popularizer who had died the previous December and who had spent decades arguing for the cultural and scientific importance of exploring other worlds. Sagan had been one of the scientists on the Viking biology team, and his insistence on taking the possibility of Martian life seriously, when many colleagues dismissed it, had shaped a generation of astrobiological thinking. Carried on the lander's ramp was Sojourner, named by a 12-year-old student who won a NASA essay contest, citing the abolitionist Sojourner Truth as her inspiration. The rover was roughly the size of a microwave oven, weighed about 11 kilograms. and drove on 6 wheels each about the diameter of a coffee mug. Its alpha-proton X-ray spectrometer determined rock and soil composition by bombarding samples with particles and measuring the energies of particles and X-rays that bounced back. Over 83 days of operation, Sojourner covered a total of about 100 meters. By the standards of what would come later, this seems almost nothing, but the rocks it analyzed told a clear story. Barnacle Bill, one of the first rocks it examined, had a silica-rich composition similar to andesitic volcanic rock on Earth. The kind of rock that forms when magma is contaminated with sedimentary material, which often implies water. Yogi, a larger, rounder boulder, had a composition consistent with basalt. Wedge and other rocks showed chemical signatures indicating weathering in the presence of water. The floodplain had once been wet. The ancient catastrophic flood had swept through a landscape where water chemistry had been actively altering rock. Pathfinder also documented the Martian weather in more detail than Viking had. Temperatures swung by more than 60 degrees between the Martian day and night. Morning winds blew consistently from one direction, afternoon winds from another. Pressure variations hinted at convective dust devils moving across the surface near the lander. Mars was a dynamic, weather-driven world, even in its current frozen state. Pathfinder fell silent in September 1997 when its battery failed. But it had proven that a rover could work on Mars, and it had renewed public interest in Martian exploration at a level that justified the far more ambitious missions that would follow. Sojourner had been designed to demonstrate a concept. The rovers that came next were designed to do science. In January 2004, 2 rovers landed on Mars within 3 weeks of each other. Spirit touched down first in Gusev Crater, a 100-kilometer wide depression south of the Martian equator targeted, because it appeared to be the floor of an ancient lake. An ancient channel, Ma'adim Vallis, had once emptied into it from the south, and orbital observations suggested water-related minerals might be present. Spirit would look for them for its first 3 months on the Martian surface. The search was frustrating. The crater floor was covered in basalt volcanic rock unremarkable in composition, showing no strong evidence of water alteration. Whatever lake might have filled Gusev in the ancient past appeared to have been buried under meters of subsequent volcanic material. Every rock spirit examined in those early months told the same story of volcanic origin with minimal water processing. It began to seem as though Gusev had been chosen poorly, that the orbital data suggesting a lake floor had been misleading, that the ancient channel emptying into the crater had perhaps been dry for so long that any record of the water it once carried had been completely overprinted. Then Spirit began driving toward a range of low hills on the crater floor called the Columbia Hills, named for the space shuttle Columbia, which had been lost on re-entry while Spirit was in transit to Mars. And everything changed. The rocks in the Columbia Hills were different. They had been exposed by erosion from whatever buried them, representing an older geological layer than the volcanic plains around them. Their textures were complex, layered, fractured, altered in ways that basalt fresh from a volcano is not. Minerals like goethite, a hydroxide of iron that on Earth forms almost exclusively in the presence of water, were present. One rock, nicknamed Pot of Gold, was so thoroughly altered by water chemistry that it barely resembled any Mars rock yet seen. Encrusted with tiny spherical features similar in some ways to the blueberries that Opportunity would find on the other side of the planet, but formed in a different chemical environment. The Columbia Hills told the story of prolonged water interaction at the time before the volcanic plains were laid down over the crater floor. The most remarkable discovery of Spirit's entire mission came in 2007 during a drive across the floor of a shallow depression, called Home Plate. One of Spirit's 6 wheels had stopped functioning properly in April 2006, and the rover had been driving backward to distribute wear, dragging the dead wheel behind it. As the broken wheel scraped across the surface, it disturbed the thin soil layer and exposed a patch of bright material beneath. The driver team noticed it in the telemetry data, flagged it, and turned Spirit around to examine what it had uncovered. The bright material was almost pure silica, silicon dioxide at a concentration exceeding 90% in places. On Earth, deposits of this kind form in only 2 environments: hot springs, where silica-rich hydrothermal water rises to the surface, cools, and precipitates its dissolved mineral load, or steam vents, where acidic steam rising through volcanic rock dissolves away everything except the silica, leaving it behind as a concentrated residue. Both environments are hydrothermal, places where hot water and volcanic rock interact. Both are among the most biologically productive environments on Earth. Deep-sea hydrothermal vents host entire ecosystems powered not by sunlight, but by chemical energy. Hot spring systems like those at Yellowstone support diverse microbial communities, including some of the most heat-tolerant organisms known. Finding the ancient Martian equivalent of these environments was the most scientifically significant thing Spirit would ever do. The silica deposit was also significant in another way. Hydrothermal environments are excellent at preserving biosignatures. When organisms die in hot springs, their cellular structures can be rapidly mineralized, replaced by silica or other minerals, while still retaining recognizable biological shapes. Some of the best preserved microbial fossils on Earth are found in ancient hot spring deposits. If life ever existed at the home plate hydrothermal site, there is a possibility that chemical or morphological traces of it might be preserved in the silica layers. No mission has yet been sent to investigate home plate in detail. It remains one of the highest priority targets for future exploration. Spirit became stuck in soft soil in April 2009 and was never freed. It operated as a stationary platform until March 2010, then went silent. Its solar panels, unable to tilt toward the winter sun from their fixed position, could not collect enough energy to survive the cold. Somewhere on the floor of Gusev crater, it still rests in the soft patch that stopped it. One wheel, half buried, tilted slightly in the direction it was trying to drive, when the soil gave way. Opportunity landed 3 weeks after Spirit, on the far side of Mars, inside a shallow crater it had not even been aiming for. Eagle crater was 22 meters wide and only 4 meters deep, barely a dimple in the flat plane of Meridiani Planum. When engineers looked at the first images, they noticed that the crater walls were banded with layers of sedimentary rock, precisely stratified in the way that only slow deposition through standing water produces, and embedded in the surface, scattered in the dust, were tiny spherical pebbles, gray against the reddish soil. Scientists called them blueberries. The blueberries were concretions, mineral deposits that form when water slowly percolates through rock and chemicals precipitate out in spherical clusters around a nucleus. On Earth, similar structures form in aquatic sediments in conditions of sustained water activity over thousands to millions of years. Their presence on Mars was unambiguous evidence that this rock had been soaked in water. The minerals in the outcrop walls confirmed it. Jarosite and iron sulfate that forms only in acidic wet conditions was present throughout the layered rock. The ancient environment at Opportunity's landing site had been wet, persistently wet, over a long enough period to chemically transform the rock at the scale of grains and crystals. Opportunity drove out of Eagle Crater and quickly found its way into Endurance Crater, a bowl about 50 meters deep and 150 meters across. The layered rock exposed in Endurance's walls extended the stratigraphic record that Eagle had begun more sulfate-rich sediment, more blueberries, more evidence of the wet acidic chemistry that had once operated at this location. The team named a particularly striking section of the Endurance Wall Burns Cliff after Roger Burns, the geochemist who had predicted before Viking that Mars might have sulfate-bearing sedimentary deposits. Burns died in 1994 without seeing his prediction confirmed. The rock that bore his name proved him right in extraordinary detail: layered, cross-bedded sandstones that had been deposited in flowing water, then chemically altered by the acidic groundwater that followed. Along the way to larger targets, Opportunity made a discovery that no rover had ever made before. It identified a meteorite, sitting on the surface of Meridiani Planum, visually quite different from everything around it. Smooth where the surrounding rocks were rough, dense where they were porous, metallic gray where everything else was red, was an iron-nickel meteorite approximately the size of a basketball. The team named it Heat Shield Rock because it had landed near the discarded heat shield from Opportunity's entry. It was the first meteorite identified on the surface of another planet. On Earth, meteorites are found by searching in places where nothing else looks like them: Antarctic ice sheets, desert pavements. On Mars, the entire surface is a desert pavement of sorts, and meteoric material has been arriving continuously for 4 billion years. How much of what Mars rovers have driven past is meteoritic in origin and recognized against the background of red rock is an interesting question. Opportunity eventually reached Endeavour Crater, a bowl 22 kilometers wide, ancient enough to predate most of the sulfate-rich geology of Meridiani, exposing rocks from an earlier Martian period with different chemistry. Here, at the cape-shaped promontory called Cape York and later at Solander Point, the rover found clay minerals, phyllosilicates, that form in neutral rather than acidic water. The water chemistry that had once been present was different from the acidic sulfate environment of Ego and Endurance, and potentially more hospitable to life. Ancient Mars had not been a uniform place. It had been geographically and temporally varied, with different water chemistries operating in different locations and at different times. Opportunity survived for 15 years. Covering more than 45 kilometers of Martian terrain, the first rover to complete the equivalent of a marathon distance on another world. It survived Martian winters by tilting its solar panels toward the weakened sun, driving against its own dead battery and the relentless dust accumulation that reduced its power generation every year. Dust devils cleaned the panels multiple times and extended its life in ways that were not planned. It endured computer memory problems, a failing actuator in its robotic arm, and the wear of decades of Martian nights on a vehicle designed for 90 days of operation. It died in June 2018 when a planet-wide dust storm the size of the one that had killed Sojourner was just the beginning of everything that had followed reduced sunlight to levels the panels could not survive. Engineers tried to make contact more than 1,000 times after the storm cleared. On the final attempt, the team transmitted 2 pieces of music in sequence. Billie Holiday's voice drifting across 200 million kilometers of space to a silent machine on a rust-colored plane. There was no reply. Somewhere in Meridiani Planum, Opportunity still sits where it stopped, coated in red dust, aimed at a sky it can no longer see. What Mars has taken from us, mission by mission, is always the same thing. The machine, what it leaves behind is the data, the images, the measurements, and the questions those measurements raise. Each rover that has died on Mars has died in the act of answering questions, and each set of answers has generated new ones more interesting than the last. Between the Pathfinder mission of 1997 and the twin rover landings of 2004, another spacecraft conducted what may have been the single most productive orbital mission in the history of Mars exploration. The Mars Global Surveyor arrived in September 1997 and spent nearly a decade mapping the Martian surface at resolutions that made every previous map obsolete. By the time it fell silent in 2006, it had returned more data than all previous Mars missions combined. Among its most consequential instruments was the Mars Orbiter camera, which took more than 240,000 images across 9 years of operation, cataloging the Martian surface at resolutions down to about 1.5 meters per pixel, sharp enough to show a vehicle the size of a car. The camera documented the Martian seasons in unprecedented detail, showing the advance and retreat of the polar caps year by year, the progression of dust storms from regional to global scale, and the subtle changes in surface albedo, the brightness of the ground, as winds redistributed dust across thousands of kilometers. The Mars Orbiter laser altimeter produced the first precise topographic map of the entire Martian surface. This map revealed something that had been suspected from orbital photography but never measured quantitatively. Mars is deeply asymmetric. The southern hemisphere is heavily cratered ancient terrain, on average about 5 kilometers higher in elevation than the smooth northern lowlands. The boundary between these two hemispheres, the dichotomy, is one of the great unsolved problems in planetary science. The leading hypothesis is that the northern lowlands were formed by a single enormous ancient impact, the largest impact event in the history of the solar system, but no confirmed impact structure has been identified beneath the sediments that fill the basin. Alternatives involving deep mantle processes, early plate tectonics, or the accumulation of ocean sediments have each found supporters and critics. The dichotomy is real, its origin remains genuinely unknown. The Mars Global Surveyor also discovered something that sent a fresh wave of excitement through the scientific community in 2000 gullies. In thousands of images of pole-facing slopes in the mid-latitudes of both hemispheres, the camera revealed freshly carved channels, gullies running from cliff tops and crater walls down to debris fans at the base of slopes, in a pattern eerily similar to gullies carved by brief, powerful flows of liquid water on Earth. They were found in regions where liquid water should not be stable under current Martian conditions, at latitudes where temperatures can drop below -100 degrees Celsius in winter. Some gullies showed color differences suggesting they were geologically recent. Later analysis determined that some had actually formed between images taken months apart during the MGS mission itself, active today. The mechanism responsible for them is still debated. Liquid brine, liquid carbon dioxide, dry ice avalanches, and granular flows have all been proposed. The mystery has still not been resolved to universal satisfaction. Planetary scientists divide Mars's history into 3 broad epochs, each named for a geographic feature that typifies its character. The oldest is the Noachian, named for Noachi's Terra in the southern highlands, spanning from the formation of the planet roughly 4.5 billion years ago to about 3.5 billion years ago. The Noachian was the age of heavy bombardment, a period when the inner solar system was thick with debris left over from planetary formation and large impacts were frequent. But it was also crucially a wet age. The ancient valley networks, the branching channels visible from orbit across much of the southern highlands, formed primarily during the Noachian. Minerals that require liquid water for their formation, clays and carbonates, are concentrated in Noachian terrain. The early Martian climate was warm enough and the atmosphere thick enough to support liquid water at the surface. Whether this warmth was continuous or episodic, maintained by a greenhouse effect or produced cyclically by volcanic activity and large impacts, remains a matter of active debate. But water was there. The Hesperian period followed from roughly 3.5 to 3 billion years ago, and it was an age of transition and violence. Volcanic activity reached its peak, building the enormous Tarsis Plateau and releasing vast quantities of gas into the atmosphere. Large-scale catastrophic flooding carved the great outflow channels, Khazau valleys, Ares valleys, Mangala valleys, releasing quantities of water that would have rivaled the largest floods in Earth's geological record. But the climate was changing. The magnetic field had already been lost. The atmosphere was thinning. The planet was cooling. Water that had once flowed on the surface was retreating underground, freezing into permafrost, concentrating at the poles. The Amazonian period began about 3 billion years ago and continues today. It is by far the longest of the three epochs, spanning most of Mars's total history, and it is the cold, dry, frozen Mars we know from our spacecraft. Volcanic activity has continued sporadically, but at a greatly diminished rate. Water has existed primarily as ice. The surface has been shaped predominantly by wind, by impacts, and by the slow seasonal cycling of carbon dioxide between the atmosphere and the polar caps. The Mars of the Amazonian is geologically quieter but not inert, and the very existence of the Amazonian epoch, stretching billions of years, raises a sobering thought. If life arose during the Noachian or Hesperian on Mars, it has had 3 billion years to either survive, adapt, or leave traces. The long silence of the Amazonian is itself a kind of data. The Martian atmosphere is the key to understanding that entire arc of transformation. At present, it is so thin that the pressure on the surface sits just below a threshold. Physicists call the triple point of water the precise combination of temperature and pressure at which water can exist simultaneously as ice, liquid, and vapor in thermodynamic equilibrium. For water, that threshold lies at 611 pascals. The average surface pressure on Mars is around 600 pascals, just barely below it. The consequence is that liquid water cannot persist on the open surface under current conditions. A drop of water placed on the Martian ground would either immediately freeze or immediately evaporate, depending on the local temperature. It cannot sit still, it cannot pool, it cannot flow. This single physical fact determines nearly everything about the modern Martian surface. No rivers, no lakes, no seas. The only water visible in the open is frozen solid. Ice is present in two main forms, locked into the subsurface soil as permafrost and exposed at the poles as permanent ice caps. The North Polar Cap of Mars is a layered structure of water ice, roughly 1,700 kilometers across in the depths of winter, shrinking to about 1,000 kilometers in summer as its outer edges sublime into the thin air. Its central dome reaches a thickness of approximately 2 kilometers. Scientists who have studied the layered deposits within it have found a record of Martian climate cycles, etched in alternating light and dark bands of ice and dust, laid down over hundreds of thousands of years as the planet's axial tilt and orbital shape shifted. The ice records the planet's past, the way tree rings record years of drought and plenty, except the timescales involved span epochs. The South Polar Cap is different in character. During winter, it accumulates a seasonal layer of frozen carbon dioxide, dry ice, that can be meters thick, covering the underlying water ice entirely. In summer, most of this seasonal CO2 cap sublimes away, but what remains beneath is a permanent layer of water ice far thinner than the northern cap, only a few hundred meters in the thickest parts. The geometry of the southern cap is also more irregular, carved by the same sublimation processes that act on it each summer into a bizarre landscape of mesa-like plateaus, pits, and channels that has been compared to a block of Swiss cheese seen from above. The Martian South Pole is one of the strangest-looking terrains in the solar system. Beneath the surface, across the broader planet, water is more abundant than the bare landscape suggests. 2 decades of orbital radar surveys by instruments aboard the Mars Reconnaissance Orbiter and the European Mars Express spacecraft have revealed substantial volumes of water ice in the Martian subsurface, particularly at middle and high latitudes. In some regions, pure water ice extends from just centimeters below the surface to depths of hundreds of meters. When meteorites strike in these areas, fresh impact craters expose bright white ice, confirming what radar has detected. One particularly striking image from the HIRIS camera showed a fresh crater only 5 meters wide with brilliant white ice exposed on its floor, ice that would have sublimed away within a few months had the camera not captured it shortly after the impact. Even at the surface, the soil carries water in chemically bound forms. When the Curiosity rover heated soil samples collected from the floor of Gale crater, instruments measured water vapor being driven off, about 2% of the sample by weight. A cubic meter of Martian soil holds something close to a liter of water. It is water that has been there for hundreds of millions of years, bound into the mineral structure of the ground and into the lattices of a mineral called perchlorate, a compound also identified by the Phoenix lander, which we will return to shortly. Among the most controversial water-related features on Mars are the recurring slope lineae, dark, narrow streaks that appear on steep slopes during the warmest Martian seasons and fade as temperatures drop. They were first identified in 2011 by Lujendra Ojha, then an undergraduate student analyzing high-rise images, who noticed that the same slopes that appeared clean in winter images showed dark tentacles of color, creeping downhill in summer, then retreating or disappearing by the following winter. The pattern repeated: summer growth, winter fading, summer growth again. The initial hypothesis was compelling. Briny water, depressed in its freezing point by dissolved perchlorates and other salts, flowing down steep sun-facing slopes during the warmest part of the Martian year. The spectral data seemed to support it. Chrism spectroscopy of active lineae detected hydrated salts consistent with material recently wet with brine. For a brief period, the scientific press wrote seriously about currently flowing liquid water on Mars. Subsequent analysis has complicated the picture significantly. The hydrated minerals detected might form from water vapor condensing onto salt-rich slopes rather than from flowing liquid. The flow patterns are consistent with dry granular flow avalanching dust or sand that preferentially occurs on slopes already enriched in hydrated salts by some independent process. More tellingly, some lineae have been found to originate not at the top of water-bearing layers, but from bare bedrock surfaces where no subsurface water source is plausible. The current scientific consensus has shifted. Most researchers now believe that recurring slope lineae are more likely granular or dust avalanche features than brine flows, though the question of whether small amounts of transient liquid water might be involved in some cases has not been fully closed. The recurring slope lineae story is itself instructive. Mars repeatedly generates features that look like water and turn out on closer inspection to have alternative explanations. The planet has a talent for mimicking habitability at first glance. Whether this is because water truly is pervasive in Martian history, expressed in the chemical alterations, the morphology, the minerals, the layering that water leaves behind even long after it has gone, or because human pattern recognition is primed to find water everywhere it looks, is a question that only more data can answer. One piece of data that generated more controversy than almost any other in the history of Mars exploration came not from a spacecraft at Mars, but from a rock sitting in a laboratory drawer in Houston, Texas. The meteorite designated ALH 84001 was found in the Allen Hills region of Antarctica in 1984, where it had lain in the ice for about 13,000 years. Its chemical composition matched the Martian atmosphere with high precision. It was unambiguously a Mars rock, ejected from the planet by an ancient impact, and eventually captured by Earth's gravity. Dating showed that the rock had crystallized from Martian magma about 4 billion years ago, solidifying during the Noachian period when Mars was warm and wet. In August 1996, a team of NASA scientists led by David McKay published a paper in the journal Science claiming that ALH 4001 contained evidence of ancient Martian life. Their evidence was fourfold: carbonate globules in the rock that formed at temperatures compatible with life, polycyclic aromatic hydrocarbons associated with biological processes on Earth, magnetite crystals identical in form to those produced by certain magnetotactic bacteria, and most dramatically tiny elongated structures in electron microscope images that looked uncannily like microbial fossils. The announcement was extraordinary. President Clinton made a statement from the White House. The front pages of newspapers around the world declared that life had been found on Mars. The Mars Pathfinder mission, which had been struggling for funding, suddenly found itself with a renewed mandate. The extraordinary claim required extraordinary evidence, and the scientific scrutiny that followed was intense. Over the following decade, each of the 4 lines of evidence was examined by multiple independent research groups and found wanting. The carbonate globules could form inorganically at high temperatures, not the mild temperatures required for biology. The PAH could be terrestrial contamination accumulated during the meteorite's long tenure in Antarctic ice. The magnetite crystals, while similar to biological magnetite, could be formed inorganically by thermal decomposition of carbonate. And the microscopic features interpreted as microbial fossils were at least an order of magnitude smaller than the smallest known organism. So small that fitting the necessary biological machinery inside them is physically implausible. By the early 2000s, the consensus had shifted to skepticism. No single line of evidence in ALH 84001 requires a biological explanation. And each has a plausible abiotic alternative. This does not mean Mars is lifeless. It means that this particular rock does not provide the proof. But the controversy transformed the field. It elevated astrobiology, the study of life's potential beyond Earth, from a fringe interest to a mainstream scientific discipline with dedicated funding, dedicated journals, and dedicated missions. The Mars Exploration Rover program, the Phoenix Lander, and ultimately Perseverance can all trace part of their scientific rationale to the questions that ALH 8401 posed in 1996, even if the rock itself failed to answer them. All of this frozen, buried, bound water is the remnant of something far larger. Mars preserves geological evidence of ancient liquid water on a scale that is almost impossible to fully comprehend without staring at the orbital imagery for a long time. The valleys carved by flowing water are not subtle features. They are vast branching networks visible from orbit, etched into terrain more than 3 billion years old. The system called Nirgal Vallis winds for more than 500 kilometers through the southern highlands. Nanyedi Vallis in Zante Terra reaches a kilometer in depth and shows in places a sinuous inner channel along its floor that could only have been carved by a sustained, continuously flowing river. The channels leading into Chris Planitia, the same region where Viking 1 landed, were cut by floods of a scale unmatched anywhere in Earth's geological record. The Hellas impact basin in the southern hemisphere presents a different kind of evidence for Mars's complex water history. Hellas is roughly 2,300 kilometers wide and about 7 kilometers deep, one of the largest impact craters in the solar system, formed by a collision early in Mars's history, energetic enough to have excavated material from deep in the Martian crust and distributed it across thousands of kilometers of surface. Because of its great depth, the atmospheric pressure at the floor of Hellas is higher than anywhere else on Mars, high enough at certain times of year for liquid water to be transiently stable at temperatures slightly above its freezing point in the lowest parts of the basin. The floor shows geological features consistent with ancient lake deposits, layered sedimentary material, channels entering from the surrounding highlands, and in some areas smooth terrain suggestive of sediment accumulated in standing water. Some researchers have proposed that Hellas hosted lakes or even a sea during warmer and wetter periods of Martian history, and that the basin's floor preserves a detailed sedimentary record of conditions that no longer exist anywhere on Mars's surface. Accessing that record, drilling through meters of surface deposits to reach the ancient lake sediments below, is a priority for future missions that are currently in the planning stages. And then there is the ocean question. Multiple independent lines of evidence suggest that sometime during the Noachian and early Hesperian periods, the northern lowlands of Mars, a region that covers roughly a third of the planet's surface and sits 3 to 5 kilometers below the southern highlands, were filled with a shallow ocean. The most compelling evidence is topographic. There are two distinct boundary features that run for thousands of kilometers around the margins of the northern lowlands at different elevations, each consistent with an ancient shoreline. Minerals whose formation requires standing water are concentrated in the northern plains. Sedimentary deposits in the lowlands have characteristics consistent with ocean floor deposition. And the pattern of ancient river channels, nearly all of them flowing northward, from the highlands toward the lowlands, is exactly what you would expect if a large body of water was collecting in the northern basin. The ancient Martian ocean, if it existed, was not like Earth's oceans. It was shallower, perhaps a kilometer deep in its deepest parts. It was colder, likely covered by ice on its surface for much of its existence. It was fed not primarily by rainfall but by catastrophic floods released periodically from subsurface ice reservoirs and by rivers fed by volcanic heating and impact-generated melt. And its shorelines would have looked strange by terrestrial standards, no tidal zones shaped by lunar gravity because Mars's small moons raise only negligible tides, no wave-cut terraces shaped by storm surf, because the thin atmosphere could not drive large waves even when the ocean existed. But it was there, water covering a substantial fraction of a world that now shows no liquid water anywhere on its surface. No feature on Mars illustrates its violent geological past more dramatically than the canyon system called Valles Marineris. It stretches across the equatorial region for roughly 4,000 kilometers, a distance comparable to the width of the contiguous United States. In places, it is more than 700 kilometers wide and descends more than 7 kilometers below the surrounding plateau. The Grand Canyon, which impresses every person who stands at its rim for the first time, is about 450 kilometers long and about 1.5 kilometers deep. Valles Marineris dwarfs it by every measurement to the point where the comparison becomes almost absurd. Valles Marineris formed primarily through tectonic stretching and faulting. The Martian crust in this region was pulled apart, similar to the way rift valleys form on Earth in regions like East Africa. The stretching was driven by the enormous mass of the Tharsis volcanic plateau immediately to the west, whose formation warped and stressed the Martian crust over billions of years. Fractures opened, blocks dropped, and the terrain collapsed to form the greatest canyon in the solar system. The process was not instantaneous. Different sections of the canyon system opened at different times, and the full extent of Valles Marineris developed over hundreds of millions of years. Water played a secondary but significant role. Once the initial fractures formed, groundwater eroded the walls and floor, landslides carried material from the canyon walls into the basins, and tributaries carved by flooding branched off from the main system in all directions. The interior of Valles Marineris contains one of the most geologically complex terrains on Mars, layered sedimentary deposits hundreds of meters thick inside the canyon floor, chaotic terrain formed by the collapse of subsurface ice, windswept dune fields, and landslide deposits covering areas of hundreds of square kilometers. Melas Chasma, one of the widest sections of the canyon, reaching depths of 9 kilometers below the surrounding plateau, contains sedimentary layers that some researchers interpret as lake deposits from a body of water that once filled part of the canyon to significant depth. If a lake existed in Melas Chasma, it would have been among the deepest enclosed lakes in the solar system, formed in the deepest accessible basin on Mars, fed perhaps by groundwater seeping through the canyon walls and by melting ice from the highland plateaus above. The chemical signatures detected by orbital spectrometers include sulfates and other minerals consistent with evaporite deposits. The residue left behind when a body of water evaporates and concentrates its dissolved minerals as salts. This same chemistry, sulfates marking the edges of vanished water, is what Opportunity found at Meridiani Planum and Curiosity found at Gale Crater. The pattern recurs across Mars at vastly different scales, in different geological contexts, tracing the contours of a world that was once far wetter than it is today. The sheer scale of Mars's geology, the volcanoes, the canyons, the ancient ocean basins, reflects a planetary history driven by forces comparable in magnitude to Earth's own geological engine, but expressed differently because Mars has no plate tectonics. On Earth, the crust is divided into moving plates that recycle old material back into the mantle and create new surface at spreading centers. The energy of the geological system is distributed across the entire planet and expressed in earthquakes, volcanoes, mountain chains, and ocean ridges spread across every ocean basin and continent. On Mars, without plate tectonics, the same internal energy accumulated in place, building individual structures to sizes that have no terrestrial equivalent. Mars has 2 moons, and both are small enough that when astronomers first began searching for them in the mid-19th century, the search nearly failed. Asaph Hall of the U.S. Naval Observatory, working in August 1877, was on the verge of giving up when his wife Angelina urged him to keep looking. He found Deimos the next night and Phobos the night after. He named them after the companions of the war god in Greek mythology, Phobos meaning fear and Deimos meaning dread. The discovery was made during a particularly favorable opposition of Mars, the closest approach between Earth and Mars in a generation. But even so, both moons were extraordinarily difficult to see. Their small size and low reflectivity meant that they appeared as barely distinguishable points of light, even in Hall's powerful telescope, hidden in the glare of the planet itself. The search had required systematic observation night after night, mapping the field around Mars in such careful detail that when a point appeared that had not been there before, that was moving in a way consistent with the moon of Mars, it stood out against the catalogued background stars. Phobos is the larger of the two, about 27 kilometers across at its widest, a lumpy potato-shaped object with a heavily cratered surface. Its most prominent feature is the Stickney crater, 6 kilometers wide and nearly a third, the total diameter of the moon itself. The impact that formed Stickney was enormous relative to the size of the body it struck, so large that it came close to shattering Phobos entirely. Fractures and groove systems radiate outward from Stickney across much of the surface. And some of these grooves are thought to be cracks in the moon's interior, rather than simple surface features. There is a growing body of evidence that Phobos is not a solid body, but a rubble pile, a collection of fragments held together by mutual gravity, with a significant fraction of its volume consisting of empty space between loosely packed boulders. If so, it is among the most porous and fragile large objects in the solar system, and any spacecraft that attempted to land on it would need to anchor itself rather than simply touching down or risk bouncing off the low-gravity surface into space. Phobos orbits Mars at an altitude of only about 6,000 kilometers, closer to its planet than any other moon in the solar system, and completes an orbit in about 7.5 hours. This means it rises in the west and sets in the east for Martian surface observers, crossing the sky in roughly 4 hours and appearing roughly 3 times per Martian day. It is too small to fully block the Sun during transits. Observers on Mars would see it as a small dark disk crossing the solar face, and both Curiosity and Opportunity have photographed Phobos transiting the Sun from the Martian surface, creating a miniature solar eclipse effect quite unlike anything seen from Earth. Phobos is getting closer. The same tidal forces that are gradually moving Earth's moon farther from Earth are doing the opposite to Phobos, because Phobos orbits faster than Mars rotates. Tidal interaction drains energy from Phobos' orbit and pulls it inward by about 2 centimeters per year, a tiny rate but one that compounds over geological time. In roughly 40 to 50 million years, Phobos will either crash into Mars or disintegrate as it crosses the Roche limit. The distance at which tidal forces exceed the gravitational cohesion holding a body together. If Phobos disintegrates rather than crashes, it will spread into a ring around Mars. Faint, temporary by geological standards, but real, Mars would briefly become a ringed planet. Deimos is smaller, about 15 kilometers wide, and orbits much farther out at about 23,000 kilometers. It moves so slowly across the Martian sky that it appears to rise in the east and take several Martian days to complete a single pass. Its surface is smoother than Phobos', possibly because the regolith, the fine surface material, is thicker, filling in craters and creating a more uniform appearance. Both moons have very low albedos. They reflect only about 6% of the sunlight they receive, making them among the darkest objects in the solar system by reflectivity. How they formed is not known with certainty. The leading theories involve either capture of asteroid belt objects or formation from debris ejected by a large impact on Mars early in the planet's history. Spectral measurements suggest compositions similar to carbonaceous chondrite asteroids consistent with capture. But captured moons should have highly eccentric inclined orbits, and both Phobos and Deimos orbit in nearly circular equatorial orbits. Reconciling this with capture requires additional dissipative processes that are physically plausible but not proven. Future missions specifically designed to visit and sample the Martian moons, including a Japanese mission called Martian Moons Exploration, targeted for launch in the late 2020s, may resolve the origin question by returning surface material for analysis. The Phoenix lander arrived at Mars in May 2008, setting down in the Arctic plains of Vastitas Borealis at a latitude of 68 degrees north, the closest to a Martian pole that any lander had ever operated. Phoenix had been built from components salvaged from a cancelled mission and carried instruments specifically designed to study the Arctic soil and search for evidence that this cold, high-latitude environment could have been, or might still be, hospitable to microbial life. The first surprise came within days of landing. Cameras mounted beneath the lander, looking down to verify that the footpads had landed securely, showed something unexpected. A flat, smooth surface where the rocket exhaust had blown away the thin soil layer and exposed what appeared to be solid ice just centimeters below the surface. Over the following days, that ice was watched carefully in time-lapse imagery, and fragments of it disappeared. subliming directly from solid to gas, exactly as water ice behaves at Martian surface conditions. The team was looking at real ice sitting in the Martian Arctic, where it had rested for perhaps millions of years, now exposed by the touchdown of a spacecraft from Earth. The robotic arm then began excavating systematically. The Arctic soil was unlike anything previous missions had sampled. It was stiff, cohesive, and clumping in ways that the loose sandy regolith of equatorial regions was not. When the arm dug a trench, the walls held nearly vertical rather than slumping. The ice beneath was cementing the soil from below. Bright fragments of ice were visible in the trench walls, vanishing over the course of hours as the Martian sun worked on them. Soil samples were delivered to miniature ovens and heated progressively, and the gases released were analyzed chemically. The results were a mixture of the expected and the surprising. The expected water vapor driven off as the ice sublimed, confirming the presence of water ice in the soil at the level of several % by weight in the top few centimeters. The surprising, the Martian Arctic soil contained perchlorates, salts of perchloric acid, at concentrations of about 0.5% by weight. This discovery reverberated through the astrobiology community for years on Earth. Perchlorates at these concentrations are toxic to most organisms. Their presence in Martian soil is a complication for any future human missions, because colonists who work with Martian soil or grow food in it without processing would be exposed to a potential health hazard. But perchlorates are not only toxic. Certain groups of bacteria on Earth, called perchlorate-reducing bacteria, use perchlorates as a terminal electron acceptor in their metabolism, essentially breathing perchlorate the way most organisms breathe oxygen. They thrive in environments where oxygen is scarce and perchlorates are available. If Martian microbes existed, perchlorate reduction would be a viable energy source. More significantly, perchlorates mixed with water dramatically depress its freezing point. A saturated perchlorate brine can remain liquid at temperatures below -70 degrees Celsius, temperatures that Mars regularly achieves at the surface. If perchlorate-rich brines exist in the Martian subsurface, they might provide a liquid water medium even today, despite surface temperatures that would freeze pure water solid. This is speculative. Direct evidence for perchlorate brines in the modern Martian subsurface has not been confirmed. But the chemistry is real, and Phoenix's discovery opened a line of investigation that continues to this day. Phoenix also confirmed what Viking had suggested and later missions had elaborated. The Martian soil is chemically unusual by Earth standards, permeated with oxidizing compounds that would rapidly destroy many organic molecules. This has a sobering implication. Even if organisms once lived on Mars and died billions of years ago, their chemical remains at the surface may have been destroyed beyond recognition by the combination of ultraviolet radiation, cosmic rays, and oxidizing soil chemistry. Any surviving biosignatures would likely need to be found at depth beneath the oxidized surface layer, where shielding has preserved the chemical record intact. This is one reason why the Perseverance rover sample coring targets the interiors of rocks rather than the surface, and why future missions capable of drilling to tens or hundreds of meters depth are considered scientifically essential. In November 2013, NASA launched a spacecraft called MAVEN, the Mars Atmosphere and Volatile Evolution Mission, specifically to study the process by which Mars has lost its atmosphere over time. MAVEN entered Martian orbit in September 2014 and has operated there since, making it one of the longest-running active Mars missions. The loss of Mars's atmosphere is intimately connected to the loss of its magnetic field, which in turn is connected to the cooling of its interior. Early in Mars's history, its liquid iron core generated a global magnetic field similar in principle to Earth's. This field deflected the solar wind, the continuous stream of charged particles flowing outward from the Sun, and prevented it from directly interacting with the upper atmosphere. The early Mars was shielded, then the core cooled. Mars is smaller than Earth, with a higher ratio of surface area to volume, and it radiates heat to space more efficiently than a larger planet would. Exactly when the core solidified is debated, but by about 4 billion years ago, the global magnetic field had largely disappeared. What remains today is not a global field, but scattered patches of magnetized ancient crust in the southern highlands. Remnants of rock that locked in the direction and intensity of the field when it existed, preserved in ancient basalt the way a recording is preserved on magnetic tape. These crustal patches are among the oldest rock on Mars, and they are the only physical record of a field that once protected a different and more hospitable world. Without the magnetic field, the solar wind began stripping the atmosphere. Maven measured the rate. Roughly 100 grams of atmosphere escape every second under normal solar wind conditions. When the Sun is particularly active during solar storms, when it ejects massive clouds of plasma called coronal mass ejections, the stripping rate spikes dramatically. During the young Sun's most active period 4 billion years ago, this process was far more intense than today. The atmosphere that Mars had in the Noachian was substantial, thick enough to sustain liquid water, thick enough to support a greenhouse warming that kept surface temperatures above freezing. That atmosphere did not simply vanish overnight. It leaked away over billions of years, thinning steadily, cooling the planet, lowering the pressure until liquid water became first unstable, then impossible. Maven has also made unexpected discoveries beyond the main loss process. It's detected layers of metal ions in the upper atmosphere. Magnesium and iron deposited by the constant rain of meteoric material entering from space. It observed ultraviolet auroras spread not just over the poles as on Earth, but across the entire disk of the planet, following the pattern of the scattered crustal magnetic patches rather than a global field. It discovered proton auroras, a type not seen on Earth, formed when hydrogen from the solar wind interacts with the upper atmosphere in a specific way. And it has captured the precise dynamics of the magnetic tail of Mars, the elongated region on the night side of the planet where the solar wind and the Martian ionosphere interact and twist, like a flag streaming downwind in a constant gale. One of Maven's most instructive observations came during a major solar storm in September 2017. A series of X-class solar flares, the most powerful category, struck Mars without the benefit of any global magnetic field to deflect the charged particles. Maven measured the atmospheric escape rate during and immediately after the storm events and found it spiking to 25 times its background level. The planet's atmosphere was being stripped away at a rate orders of magnitude higher than on a quiet day. Extrapolating similar events back to the early solar system when the Sun was more active and such storms were more frequent and more intense gives a quantitative picture of how rapidly Mars must have lost its early atmospheric inventory. The ancient atmosphere that supported liquid water was not gradually thinned over billions of years by the quiet, continuous solar wind we measure today. It was pulverized episodically by a young star in its most active phase, lost in great bursts whenever the Sun erupted, each event stripping away a thin layer that would never be fully replaced. Running in parallel with Maven's atmospheric research, the European Space Agency's ExoMars Trace Gas Orbiter arrived at Mars in 2016, though its accompanying demonstration lander, Schiaparelli, crashed on the Martian surface when a software error caused the onboard computer to believe it had already landed when it was still over a kilometer up. The retrorockets cut off prematurely. Schiaparelli hit the surface at over 300 kilometers per hour, and the impact was photographed from orbit by the high-risk camera as a dark smear on the Martian plain, a reminder that landing on Mars is one of the most difficult operational challenges in spaceflight, and that nothing about it can be taken for granted, regardless of how many times it has been done successfully before. The Trace Gas Orbiter itself operates successfully, equipped with instruments specifically designed to detect atmospheric gases at very low concentrations, precisely the capability needed to settle the methane controversy. Its NOMAD and ACS spectrometers have placed strict upper limits on atmospheric methane of below 50 parts per trillion, far below the levels that Curiosity reported from the surface. This apparent contradiction between the rover's measurements and the orbiter's upper limits has not been resolved and remains one of the most puzzling open questions in current Mars science. Either Curiosity is detecting something the orbiter cannot see because the methane is extremely locally distributed and rapidly destroyed near the surface, or one of the measurement systems has a systematic error not yet identified. Resolving this discrepancy is a high priority for the atmospheric science community. Understanding atmospheric laws does not only illuminate the past, it bears directly on the future. Any serious plan to eventually thicken the Martian atmosphere to warm the planet toward conditions where liquid water could persist must account for the fact that the solar wind is still stripping atmosphere away at rates measurable by spacecraft today. Whatever you add, the wind will take. The timeline of any terraforming effort must be measured against this continuous loss. Terraforming Mars is an idea that scientists and engineers have taken seriously at least since the 1970s, when Carl Sagan and others first published analytical papers on the subject. The basic concept involves releasing enough greenhouse gases into the Martian atmosphere to warm the planet, triggering the sublimation of carbon dioxide ice from the polar caps and the soil, which would further warm the atmosphere in a runaway greenhouse cascade, eventually raising temperatures and pressure enough that liquid water could persist on the surface. Various mechanisms have been proposed to start the cascade. Orbiting mirrors to focus sunlight on the polar caps, factories on the surface producing powerful greenhouse gases, such as perfluor or carbons, redirecting asteroids rich in volatile compounds to impact Mars and deliver raw atmospheric material. Most serious analysis of these proposals conclude that Mars does not have enough accessible carbon dioxide in its polar caps, in the soil, and in its minerals to produce an atmosphere thick enough to support liquid water, even if all of it were released. The planet has simply lost too much of its original volatile inventory to space over 4 billion years. A thickened atmosphere might be achievable with sustained effort over centuries, sufficient to raise surface pressure and allow temperatures to rise, but achieving Earth-like conditions would likely require importing vast quantities of material from elsewhere in the solar system. Terraforming Mars fully is not a project for a generation, or even for a millennium. It is a project for deep time, requiring a civilization prepared to commit to a plan measured in thousands or tens of thousands of years. Whether such an endeavor would be ethically justified is a separate question, and one that the discovery of any extant Martian life, however microbial, would immediately transform. Terraforming a barren planet is one thing. Terraforming a biosphere is another. The answer to the question of whether Mars is alive would determine whether Mars is ours to change. Olympus Mons stands on the Tharsis Plateau as the single most extreme landform in the solar system. It is a shield volcano, and it is large enough to constitute its own climate zone. Its base diameter is approximately 600 kilometers, wide enough that if you placed it over France, its edges would extend past every border. Its summit stands about 22 kilometers above the Martian datum. Measured from its base to its summit, its total relief exceeds 25 kilometers. No mountain on any planet or moon comes close to those numbers. It formed because Mars has no plate tectonics. On Earth, volcanic hotspots produce chains of islands, the Hawaiian chain, for instance, as the tectonic plate carries the crust over the stationary mantle plume, So each volcano has only a limited time over the hotspot before it is carried away. On Mars, the crust has not moved. The farthest hotspot has been erupting in essentially the same location for 3 to 4 billion years, stacking lava flow upon lava flow, building the structure higher and wider with each eruption. The most recent lava flows on the flanks of Olympus Mons, identified by crater counting that can estimate ages from impact statistics, are estimated to be less than 25 million years old, geologically recent. There is genuine scientific discussion about whether Olympus Mons might still be volcanically active, whether eruptions have occurred within the last million years or could occur again in the future. Olympus Mons is not alone. 3 other large shield volcanoes, Ascraeus Mons, Pavonis Mons, and Arsia Mons, stand in a line to its northeast, each roughly 20 kilometers tall, arranged along the crest of the Tharsis Ridge. The alignment is not coincidental. All 4 volcanoes likely formed over the same mantle plume or along the same zone of lithospheric weakness, erupting at different rates and to different final sizes as the local geology varied. Together, they constitute one of the great geological spectacles of the solar system, a chain of colossal mountains strung along a planetary ridge, visible in silhouette from Earth through a good telescope during favorable oppositions. The flanks of Olympus Mons slope at an average of about 5%, a gradient so gentle that walking up the volcano's outer face would feel, for most of the journey, like walking on flat ground. The horizon would look horizontal, the curvature of the planet would hide the summit from view even from far down the slope. Only the barely perceptible tilt of the surface underfoot would indicate that you were climbing. At the edge of the volcano's base, the terrain drops abruptly. A cliff, the escarpment encircles the entire base of Olympus Mons, reaching heights of up to 8 kilometers in certain sections. 8 kilometers is roughly the elevation of Mount Everest's summit above sea level. This wall separates the volcanic plateau from the surrounding plains, and its formation is not fully understood. One hypothesis involves gravitational spreading of the volcanic structure under its own enormous weight, causing the edges to peel away from the surrounding terrain. Another invokes erosion by ancient glacial ice or liquid water that undercut the lava flows at the margin. A third involves collapse of the escarpment sections in enormous landslides that periodically stripped away chunks of the volcano's edge. Whatever the mechanism, the escarpment is real, vertical, and daunting. Above the escarpment, the summit caldera complex is a nested series of overlapping collapsed craters. At least 6 distinct calderas formed at different times, as the underlying magma reservoir emptied and the summit subsided. The whole complex is roughly 80 by 60 kilometers across and up to 3 kilometers deep. Standing at the caldera rim and looking across its width, you would be looking across a distance greater than the length of the Rhine. The caldera floor, billions of tons of collapsed rock, is itself vast enough to contain multiple smaller geological features, lava channels, fractures, smaller collapse pits within the larger ball. The lava flows that built Olympus Mons have an additional scientific significance for any future human exploration of the planet. As basaltic lava flows cool, the outer surface solidifies while the interior continues to flow. When the interior finally drains, it can leave behind a hollow tube, a lava tube, whose roof is thick enough to provide significant structural integrity. On Earth, lava tubes range from meters to tens of meters in diameter. On Mars, the combination of lower gravity, which allows lava to flow faster and farther, and higher eruption volumes, is expected to produce lava tubes far larger than any on Earth, potentially hundreds of meters or even kilometers in diameter. Orbital imagery of the Tharsis region and the flanks of Olympus Mons shows what appear to be chains of collapsed pits, sinuous depressions where tube roofs have caved in, suggesting that enormous empty tubes run beneath the surface of these volcanic terrains, A lava tube with a diameter of 100 meters and a roof 10 meters thick would provide radiation shielding comparable to the protection offered by Earth's magnetosphere and atmosphere combined. Its interior would be thermally stable, protected from the wild temperature swings of the Martian surface. And it would be structurally ready-made, a shelter requiring only sealing at both ends to become a habitable pressurized volume. Future planners of Martian settlements have taken lava tubes seriously as candidate sites for the first long-duration human habitation on Mars, and robotic precursor missions to evaluate specific tube systems in detail are under active discussion. From the summit of Olympus Mons, the atmosphere of Mars would be almost entirely below you. The pressure there is less than 1% of an already thin surface atmosphere. In practical terms, the summit sits in near vacuum. Stars would be visible in the daytime sky. The curvature of the planet would be apparent. Below, in the deep distance, the volcano's flanks would slope away into a haze that is partly dust and partly the sheer quantity of air that even Mars' thin atmosphere interposes over 600 kilometers of horizontal distance. Any expedition to climb Olympus Mons lies in the far future. In the history of human ambition, it is not yet imaginable in concrete engineering terms. But the mountain is there, permanent, waiting. The largest thing waiting to be climbed anywhere in the known solar system. At some point in the decades ahead, the precise timing depends on funding, political will, and the pace of technological development. Human beings will attempt to reach Mars. The planning for this is already underway in several countries and in private industry. The broad architecture of how such a mission might work is constrained by physics in ways that have been understood since the early days of orbital mechanics. The journey takes between 6 and 9 months depending on trajectory and the relative positions of the planets. The two planets align for efficient travel only every 26 months, the synodic period creating a launch window that closes and opens on a fixed schedule. Miss the window and you wait more than 2 years for the next one. During the transit, the crew is exposed to cosmic radiation, high-energy particles from the galaxy, at rates that no practical shielding can reduce to currently accepted safety levels. The estimated radiation dose for a 6-month transit, based on measurements taken during Curiosity's own journey to Mars aboard the Mars Science Laboratory, is around 300 millisieverts, roughly 10 times the annual dose limit for radiation workers in most countries, and a substantial fraction of the lifetime career limit that space agencies currently apply. On the Martian surface, the radiation is somewhat better than deep space, because the planet's bulk shields the lower hemisphere and the thin atmosphere absorbs some incoming particle flux. But without the global magnetic field that protects Earth's surface, colonists would still receive annual doses several times higher than permitted under current standards. The practical solution is underground habitation. Mars has lava tubes, ancient volcanic conduits formed when the outer surface of a lava flow cooled and solidified while the molten interior drained away, leaving empty tunnels. Martian lava tubes are expected to be far larger than Earth's lava tubes because the lower Martian gravity allows lava to flow faster and farther, creating longer, wider voids before the surface crust forms. Some orbital observations have identified what appear to be lava tube skylights, circular pits where the roof has collapsed in the Tarsis region. A lava tube with a diameter of 100 meters and a roof 10 meters thick would provide radiation shielding equivalent to a substantial thickness of soil and would offer ready-made pressurized living space requiring only sealing at its ends. Living underground on Mars is not a concession to failure. It is the engineering rational choice. The food challenge is equally fundamental. A crew of 6 on Mars for 2 years requires roughly 8,000 kilograms of food if no local production is possible. An enormous mass to transport from Earth. Growing food on Mars would reduce this mass requirement dramatically, but it requires addressing multiple constraints simultaneously. The Martian soil contains perchlorates toxic to most plants at the concentrations present, requiring either washing or bioremediation before agricultural use. The light levels are lower than on Earth. Mars receives about 40% as much sunlight per unit area, meaning artificial lighting would supplement or replace natural light in enclosed growing facilities. Crops chosen would maximize caloric yield per unit of floor area. Potatoes, soybeans, wheat, and leafy greens are studied candidates. Some nitrogen-fixing bacteria, which on Earth convert atmospheric nitrogen into a form plants can use, can operate with the atmospheric nitrogen available on Mars, potentially enabling a biological nutrient cycle that reduces dependence on Earth-supplied fertilizers. The communications delay is a less obvious but equally demanding constraint. At the closest approach between Earth and Mars, signals take about 3 minutes each way. At maximum distance, the delay reaches 24 minutes each way. Mission control on Earth cannot manage real-time emergencies on Mars. Every crew on a Mars mission would need complete self-sufficiency in its medical, engineering, and operational decisions. The psychological impact of this isolation has been studied in analog environments, Antarctic stations, submarine deployments, and long-duration confinement studies. The results consistently show that isolation, confinement, and communication delay create psychological stresses that are distinct from and additive to the physical challenges of extreme environments. Group dynamics deteriorate in predictable ways, leadership becomes contested, minor interpersonal conflicts become magnified, the sense of being disconnected from the broader human world accumulates as a specific form of psychological burden. Crews on Mars missions will need not just technical expertise, but psychological resilience and compatibility that current selection processes are only beginning to systematically assess. The governance of a Mars settlement is a question that legal scholars and political scientists have begun to consider seriously. The Outer Space Treaty of 1967, to which most spacefaring nations are signatories, prohibits national appropriation of celestial bodies. No nation can claim Mars as its territory. But the treaty says nothing definitive about private settlements or the jurisdiction applicable within them. A colony on Mars, unreachable in real time from Earth and increasingly self-sufficient over time, would develop its own practical governance, whether or not any formal legal framework anticipated it. The historical precedent of Antarctic research stations, communities of people from multiple nations operating under the Antarctic Treaty System, offers a partial model. Though Antarctic stations have never had to manage resource extraction, property rights, or reproduction in the way a permanent settlement would. The legal architecture of a Martian civilization does not yet exist. It will have to be invented, probably by the people who need it. In November 2018, the InSight lander set down on the flat plains of Elysium Planitia and spent 4 years listening to the interior of Mars with the most sensitive seismometer ever deployed on another planet. Before InSight arrived, the most dramatic claim about Martian subsurface water had come from orbit. In 2018, scientists analyzing radar data from the MARSIS instrument aboard the European Mars Express spacecraft announced they had detected what appeared to be a body of liquid water beneath the South Polar ice cap. A bright radar reflection from approximately 1.5 kilometers below the ice surface, consistent with the behavior of radar waves reflecting off liquid water. On Earth, similar airborne radar signals have revealed hundreds of subglacial lakes beneath the Antarctic ice sheet, some of them harboring microbial ecosystems isolated from sunlight for millions of years. The Martian signal attracted enormous attention. Subsequent analyses complicated the picture. Additional bright reflections were found at other subsurface locations. Some researchers argued the temperatures in that region should be cold enough to freeze water even under ice pressure, requiring extremely salty brines or the presence of special mineral phases to explain liquid water. Others proposed the reflections were artifacts of particular clay or mineral compositions that mimic liquid water in radar data. The question remains genuinely open. The stakes of answering it correctly are high enough that the debate will continue until a mission capable of directly sampling the region, which does not yet exist, can make a definitive measurement. What InSight found was equally consequential, if less dramatic. It detected more than 1,300 seismic events during its operational lifetime. The largest had a magnitude of approximately 5, striking in May 2022 and sending seismic waves reverberating through Mars for nearly 6 hours. By analyzing how those waves traveled through different layers of the planet's interior, scientists were able to constrain the size of the Martian core, found to be liquid and larger than some models predicted, with a radius of roughly 1,830 kilometers and the thickness of the crust. The crust results were particularly striking. Unlike Earth, which has an oceanic crust about 7 kilometers thick and a continental crust averaging about 35 kilometers, the Martian crust appears to be uniformly thick at roughly 60 to 70 kilometers on average, with some regions in the southern highlands potentially reaching 90 kilometers. This thick crust is consistent with a planet that has not recycled its surface through plate tectonics, allowing the ancient crust to accumulate to great thickness without being subducted back into the mantle. It is also consistent with the fact that Martian volcanoes can grow to the enormous heights they do. The thick crust can support the weight of a structure like Olympus Mons without it sinking into the mantle the way Hawaiian Islands eventually do. The seismic data also revealed something about the mantle that was not expected: evidence of ongoing convective activity in the form of seismic wave attenuation patterns that suggest the deep Martian interior is warmer and more mobile than a geologically dead planet would show. Mars is seismically alive. It generates Marsquakes not just from cooling-related contraction, but from active geological processes in its interior. The implications for future human habitation are practical. Seismic risk on Mars is real, and any structures built on the surface will need to be engineered to withstand it. InSight went silent in December 2022 when its solar panels, progressively buried under settling dust, could no longer generate enough power to keep its electronics warm through the Martian night. It had transmitted science data for 4 years, data that geophysicists will be mining for decades to build a complete picture of the deep Martian interior. The Perseverance rover landed in Jezero crater in February 2021 and has been working there since. Jezero is a former lake, a crater that was once filled with water fed by a river entering from the northwest through a clearly visible ancient delta. The delta is the primary scientific target. River deltas on Earth are among the most productive environments for preserving organic material and potential biosignatures. Because sediment carried by water rapidly buries organic compounds, protecting them from ultraviolet radiation and oxidizing surface chemistry. If ancient life existed on Mars and left chemical traces, a delta deposit like the one in Jezero is among the most promising places to look. Perseverance carries instruments designed specifically for this search. Its Sherlock spectrometer uses ultraviolet laser pulses to detect and map organic compounds at millimeter scales. Its Pixel instrument uses X-rays to determine chemical composition at grain-level resolution. Together, they have detected organic molecules in multiple rock samples, not biological signatures by themselves, since organic chemistry occurs through purely geological processes as well, but chemical complexity worth preserving and returning to Earth for analysis with far more powerful tools than any that can be miniaturized into a rover. The specific geology of Jezero crater adds scientific context to every measurement. The delta at the western margin of the crater represents a river system that flowed for perhaps hundreds of thousands of years, transporting sediment from the watershed beyond the crater rim and depositing it as it slowed entering the standing water. This ancient river carried material from a large catchment area, potentially hundreds of square kilometers of diverse terrain, concentrating it in the delta deposits. Whatever organisms may have lived upstream, whatever organic compounds may have formed in the broader watershed, the delta is where the evidence would accumulate, where the sediment would bury and preserve it. Perseverance has found that the delta is not simply a pile of sediment as simple models might predict. It contains carbonate rocks, minerals that on Earth form almost exclusively in water, particularly in relatively warm, neutral pH water compatible with life, interbedded with sandstones and finer materials. The presence of carbonates is particularly significant because they tend to preserve organic material effectively, and because the conditions under which they form are among the most favorable for biological activity. The oldest carbonate-bearing rocks in the Jezero Delta would have formed when the lake was young and the river was most active, potentially during the most habitable period in Martian geological history. The rover has also found olivine-bearing rocks on the crater floor, beneath the later lake sediments, rocks that date from before the lake formed, from a period when the crater was simply a depression being filled with volcanic material from the Tharsis region. Olivine is a mineral that reacts with water to produce serpentine and other minerals, through a process called serpentinization, releasing hydrogen as a byproduct. Hydrogen is a usable energy source for microbial life, and serpentinization is hypothesized to be a possible energy source for life in subsurface environments on Mars, Europa, Enceladus, and other worlds, where water meets rock in the absence of sunlight. Finding olivine in the Jezero crater floor adds one more potential energy pathway to the inventory of habitable possibilities that Mars may once have offered. The rover has cached more than 20 sample tubes, each holding a small cylinder of Martian rock or atmosphere, each labeled and precisely located. They sit on the Jezero surface, waiting for a future mission to retrieve, launch into Mars orbit, rendezvous with a return vehicle, and carry back to Earth for study in specialized laboratories. That sample return mission is planned for the 2030s. When those samples arrive, they will be the most scientifically valuable rocks ever placed in human hands, provided they were collected with the care and precision that Perseverance has been engineered to apply. Perseverance also carried a companion that no mission had ever attempted before, a small helicopter named Ingenuity. It weighed 1.8 kilograms and spanned about 1.2 meters blade tip to blade tip, a machine about the size and weight of a large domestic bird. It was sent as a technology demonstration expected to make 5 flights over 30 days. The first flight, on April 19, 2021, lasted 96 seconds. Ingenuity rose 3 meters above the Martian surface, hovered, rotated, and landed. Every one of those 96 seconds represented years of engineering and testing in vacuum chambers on Earth that simulated the Martian atmosphere. Flying on Mars requires spinning rotor blades at more than 2,500 revolutions per minute, about 5 times faster than a typical Earth helicopter. Because the air density at the Martian surface is equivalent to Earth's atmosphere at about 35 kilometers altitude, far above any conventional aircraft ceiling. Everything about Ingenuity was optimized for this extreme. The blade design, the counter-rotating rotor configuration, the lightweight carbon fiber construction, the small onboard computer running navigation algorithms derived from self-driving car technology. When the telemetry confirming the first successful flight arrived at mission control, engineers celebrated with the specific intensity of people who had just demonstrated powered, controlled flight on another planet for the first time in history. Ingenuity went on to make more than 70 flights before a landing in early 2024 damaged its rotor blades beyond repair. Along the way, it transitioned from technology demonstration to operational scout, flying ahead of Perseverance to photograph terrain the rover would later traverse, identifying scientific targets, and mapping the ancient delta in detail impossible from the ground. It photographed Perseverance from above, a rover on Mars seen from a helicopter on Mars. It provided the engineering foundation for far larger aerial vehicles planned for future missions. A proposed rotorcraft capable of picking up cached sample tubes and delivering them to a launch vehicle is part of the Mars sample return architecture. Ingenuity showed that such a vehicle is physically achievable. The rest is engineering. Perseverance arrived at Mars in a remarkable convergence. 3 missions from 3 different countries reached Mars within days of each other. In February 2021, all launched during the same planetary alignment window. The Emirates Mars mission, called Hope, entered orbit on February 9th, becoming the first interplanetary mission from any Arab nation. Hope carries instruments to study the Martian atmosphere globally and simultaneously at all altitudes, providing the kind of planet-wide meteorological context that no previous mission had been designed to deliver. It has observed Martian weather systems evolving in real time, tracked dust storm development, and measured how gases are distributed through the atmosphere across full seasonal cycles. China's Tianwen-1 entered orbit the following day and deployed the Zhurong rover to the surface in May 2021, making China only the 2nd nation to successfully operate a rover on Mars. Zhurong landed in Utopia Planitia, the same broad basin where Viking 2 had set down 45 years earlier. Its ground-penetrating radar found evidence of hydrated minerals, water-bearing compounds, in the shallow subsurface, potentially formed by liquid water activity far more recently than the ancient wetness documented elsewhere. After about a year of operation, Zhurong entered the planned winter hibernation and had not revived at the time of this narration. From orbit, 8 spacecraft currently map and monitor the Martian surface and atmosphere. The Mars Reconnaissance Orbiter's high-rise camera resolves features smaller than a dining table, and it has used this resolution to photograph avalanches on polar scarps in progress, fresh impact craters formed during its operational lifetime dune fields that have measurably migrated from one season to the next, and every rover and lander that has reached the Martian surface since MRO's arrival in 2006. A particularly iconic image captured the Curiosity rover as a tiny dot on the lower flank of Mount Sharp, casting a long shadow on the red surface, giving a human sense of scale to a landscape normally comprehensible only in geological terms. The Curiosity rover, operating in Gale Crater since August 2012, has climbed through layered geological history preserved in the flanks of Mount Sharp. Near the crater floor, it found mudstone deposited in a long-lived lake, a body of water that persisted for perhaps millions of years with chemistry that was neutral and potentially compatible with life. Higher up the climb, sulfed minerals appeared, salts left behind as water evaporated and brines concentrated. In late 2022, Curiosity documented wave ripples preserved in rock at the floor of a section it was crossing. Oscillating textures formed in shallow water less than a meter deep, frozen in stone more than 3 billion years ago. These are among the oldest wave ripples ever identified on any planet, a record of a moment in Martian history, when a lake leapt at a shoreline that no longer exists. Curiosity has also provided the most direct atmospheric chemistry measurements from the Martian surface. Its tunable laser spectrometer has detected methane in the Martian atmosphere at the level of a few parts per billion. The detection is controversial. Some orbital measurements from Mars Express have also shown methane, while others from the ExoMars Trace Gas Orbiter have placed strict upper limits on methane abundance. But if the Curiosity measurements are correct, their implications are significant. Methane is destroyed rapidly in the Martian atmosphere by ultraviolet radiation, with a lifetime of only a few hundred years. If it is present today, it must be continuously produced. On Earth, the vast majority of atmospheric methane comes from microbial metabolism. On Mars, geological production by reactions between water and certain iron-bearing rock types, a process called serpentinization, is a plausible alternative that requires no biology. The methane question has not been resolved. What makes it particularly difficult is that the measurements at issue are near the detection limits of current instruments, and systematic errors are hard to exclude. The definitive answer will require either a more sensitive instrument at the surface or a sample return mission that allows methane concentration to be measured in Earth-based mass spectrometers with far greater sensitivity than anything that can be sent to Mars. Curiosity also detected complex organic molecules preserved in ancient Gale crater, mudstone, thiophens, benzene, toluene, and small carbon chains that on Earth are commonly produced by biological processes but can also form without biology under certain geochemical conditions. The presence of organics in the rock is not itself evidence of life. Organics rain down on Mars continuously as meteoritic material and can form through hydrothermal chemistry. But the specific distribution and complexity of the molecules found is consistent with what would be expected if ancient Martian sediment had once contained biological material that was then chemically degraded by the radiation and oxidizing chemistry of billions of years of Amazonian conditions. The organics that Curiosity found are consistent with, but do not prove, ancient biology. They're exactly the kind of ambiguous signal that sample return is designed to resolve. In February 2023, Curiosity observed something rarer still from its position in the ancient crater: rays of sunlight filtering through high-altitude clouds at sunset, beams of light refracting through ice crystals in thin formations far above the surface. Sun rays on Mars are a consequence of the same optical physics that produces them on Earth, light scattering around the edges of clouds, but on Mars the phenomenon occurs under different conditions. The clouds Curiosity photographed were unusually high, cold enough to be composed not of water ice but of frozen carbon dioxide, dry ice clouds in the Martian sky catching the last of the sunlight as the planet rotated them into shadow, perhaps the most beautiful image that rover has sent home. As autumn comes to the northern hemisphere, thin water ice clouds form in the atmosphere and precipitation slowly begins. Snowflakes of water ice that on Earth form with six-sided symmetry, but on Mars form cubic crystals, because the molecular arrangement of Martian ice differs from terrestrial ice at the temperatures and pressures involved. At the poles, the temperatures plummet to minus 125 degrees Celsius, cold enough for carbon dioxide itself to condense out of the atmosphere as dry ice. Carbon dioxide snow falls in polar winter, particles smaller than the width of a human hair, settling slowly through the near-vacuum air. Spring on the poles is violent in its own way. As sunlight returns and begins warming the surface, the transparent carbon dioxide ice allows solar energy to penetrate and warm the dark material beneath. Pressure builds under the ice until it vents explosively, erupting through cracks and sending fans of dust and gas onto the ice surface, pointed in the direction of the wind at the moment of eruption. From orbit, these fans create intricate directional patterns across the pale winter surface, each one a record of a brief, violent moment of sublimation, all of them temporary, all of them erased by the following winter snowfall. What happens in between winter and spring at the polar caps is among the most visually striking phenomena that orbital cameras have documented. As the transition progresses, the carbon dioxide ice takes on intricate forms, not the uniform flat sheet of winter, but an eroded, pitted, sculpted surface carved by the same sublimation that will eventually remove it entirely. The Swiss cheese terrain, as it has been informally called, develops pits and mesas carved by differential sublimation, where dark patches absorb more sunlight and sublime faster, creating circular depressions that grow year by year. The layered polar deposits exposed in cliffs at the margins of the caps show alternating bands of ice-rich and dust-rich material that represent tens of thousands of years of Martian climate history. A record of how the planet's axial tilt and orbital eccentricity have varied over time, cycling between periods of greater and lesser warming in a pattern analogous to the Milankovitch cycles that drive ice ages on Earth. These polar records have allowed scientists to reconstruct the recent climate history of Mars in remarkable detail. The obliquity of Mars, the tilt of its rotation axis, is not stable over long time scales the way Earth's is. Earth's tilt is stabilized by the gravitational influence of the Moon, keeping it within a narrow range around 23.5 degrees over millions of years. Mars has no large moon and its tilt oscillates chaotically between about 15 and 35 degrees over cycles of millions of years, with occasional excursions to even more extreme values. When Mars's tilt is high, the poles receive more sunlight in summer and the polar caps partially melt, releasing water vapor into the atmosphere and potentially making conditions elsewhere on the planet briefly more hospitable. The layered records in the polar ice caps preserve this history in their stratigraphy, and reading it gives planetary scientists a window into Martian climate variability that goes far beyond what any individual mission measurement can provide. The wind on Mars shapes everything it touches. The atmosphere is thin but moves almost constantly. And over geological time, even a thin flow of gas carrying fine particles has sculpted the landscape profoundly. The great dune fields surrounding the polar caps, dark rippled expanses visible from orbit, are made of basalt sand transported from volcanic source regions by wind over hundreds of millions of years. Individual dunes migrate measurably from one year to the next. Radar measurements have tracked specific dune features moving across their basins, confirming that the surface of Mars is not static even today. Dust devils are common across much of Mars during the warmer seasons, and on Mars they grow to sizes that would be extraordinary by terrestrial standards. The tallest observed from orbit have reached heights of 8 kilometers, extending from the surface into the lower atmosphere like thin, dark columns. They travel for tens of kilometers, and where they pass, they scour away the thin, bright dust coating the darker surface, leaving dark streaks that can persist for months before the next dustfall covers them. The Spirit rover had its solar panels cleaned multiple times by passing dust devils, each one restoring power generation by sweeping away the accumulated layer of fine red particles. Without those cleanings, Spirit would have died years earlier than it did. Once or twice per decade, regional storms intensify into global events. The planet-wide storm of 2018, which killed Opportunity, was the most severe in 15 years. From orbit, Mars disappeared under a uniform reddish haze within weeks, as wind lifted hundreds of millions of tons of dust into the upper atmosphere and distributed it globally. The dust absorbed solar radiation high in the atmosphere, warming it, while at the surface temperatures fell because sunlight could not penetrate. The storm was self-sustaining for months because the dust drove the atmospheric circulation that kept it aloft. Then, gradually, it settled. Mars re-emerged. Every surface it covered, the rover tracks the delicate rippled patterns in sand, the thin frost deposits was buried under a fresh, even layer of red. Global dust storms on Mars are one of the most important phenomena the planet exhibits from the perspective of future exploration, and understanding them is a priority for Mars weather science. They develop through a feedback mechanism. Regional dust lifting by strong winds creates temperature gradients in the atmosphere, which drive stronger winds, which lift more dust. Once the process reaches a threshold, it can spread over an entire hemisphere within days. The seasonal trigger is typically the southern hemisphere summer. When Mars is near perihelion, its closest approach to the Sun, and receives about 40% more solar energy than at aphelion. The increased energy drives stronger thermal gradients, stronger winds, and more dust lifting. Not every perihelion season produces a global storm, which means some additional triggering factor is involved that scientists have not yet identified with certainty. Predicting when a regional storm will escalate to global scale is currently impossible more than a few days in advance, a critical limitation for any crewed surface mission where a global storm that cuts solar power to near zero for months would be a mission-threatening event. The long-term record of dust storms, assembled from decades of orbital observations, shows that global events occur on average once every 3 to 4 Martian years, though the recurrence interval is highly variable. The climate models that simulate Martian dust storms are improving with each new dataset, but the complexity of the feedback processes involved means that accurate long-range forecasting remains a research challenge rather than an operational capability. When humans live on Mars, they will need to be prepared to survive global dust storms with whatever power reserves they can store nuclear power. As mentioned earlier, being the most robust option precisely because it is independent of sunlight. The red color that names and defines Mars comes from iron oxide, hematite, and goethite in the ubiquitous surface dust. The same chemistry that makes rust red on Earth makes Mars red from space. But the story of that redness is itself a compressed history of the planet. The iron in Martian dust was originally part of iron-bearing silicate minerals in volcanic rock, olivine, pyroxene, basalt that formed as magma cooled billions of years ago. Those minerals, when exposed to liquid water in the ancient Noachian and Hesperian environments, underwent chemical weathering. Water dissolved the silicates, released the iron, and allowed it to oxidize into the rust-colored compounds that now color the entire planet. This oxidation required both water and an oxidizing environment, conditions that Mars once had and no longer fully has at the surface, but whose chemical products have endured long after the water that made them possible disappeared. The dust itself is extraordinarily fine particles, ranging from a fraction of a micrometer to a few micrometers in diameter, small enough to remain suspended in the thin Martian atmosphere for months during global storms, small enough to infiltrate the finest mechanical joints of rover instruments and over time degrade their function. The iron in the dust gives Mars its color from a distance of billions of kilometers. It colored the sky for the Viking landers, for Pathfinder, for Spirit and Opportunity, for Phoenix and Curiosity and Perseverance. Every human artifact that has ever reached the Martian surface has been touched by this dust, coated by it, gradually buried in it. The dust is the planet's most comprehensive record of its own geological past, billions of years of weathering distilled into particles small enough to float in an almost non-existent wind, distributed globally, coloring everything the same shade of rust. The sky on Mars is not blue as it is on Earth. It is a pale butterscotch, sometimes yellowish pink, sometimes closer to brown, depending on how much dust is suspended in the air at any given time, and at what angle the sunlight strikes it. The sunsets are the reverse of Earth's, while Earth's sunsets redden because short wavelength blue light scatters away along the long path through the atmosphere near the horizon. On Mars, the dust particles are the right size to preferentially scatter red light. So the sky near the setting sun turns blue, a cold, pale, dusty blue that lasts for hours after the sun has gone below the horizon, because the fine particles suspended in the atmosphere continue to scatter and redirect what little sunlight reaches them long after the direct disk has set. Every rover that has photographed a Martian sunset has captured this blue corona around the point where the sun went down, and it is among the most otherworldly images Mars has sent back. familiar and strange at the same time. A sky that follows the right physics but produces the wrong colors. The iron that makes Mars red is a chemical record of water that no longer exists. Every grain of hematite is a fossilized reaction, a molecule of water that met a molecule of iron silicate billions of years ago and transformed both. The planet is colored by its own history. Everything about Mars is colored by its history. Has it been lifeless for 3 billion years since its oceans retreated and its atmosphere thinned? Or does something persist, clinging to briny water in deep subsurface aquifers, metabolizing chemical energy in cold, dark rock, completely beyond the reach of any instrument yet deployed on the surface? The candidate environments for extant Martian life, if it exists, are not on the surface. The surface is hostile, bathed in ultraviolet radiation that destroys organic molecules in hours, oxidized by perchlorate chemistry that would disrupt most known biological processes, frozen at temperatures that only the most cold-tolerant organisms on Earth could endure, and completely desiccated except for the brief seasonal periods when temperature and pressure allow tiny amounts of water vapor to condense. No life we know of could live on the open Martian surface today. But a few kilometers down, the picture changes. Temperature increases with depth on any rocky planet. Mars is no different. And models of the Martian subsurface suggest that at depths of perhaps 5 to 10 kilometers, temperatures may be warm enough for liquid water to exist year-round, provided that dissolved salts depress the freezing point sufficiently. At those depths, the pressure is high enough to make liquid water stable, even in Mars's low atmospheric pressure environment. The rock is dark and cold, but it is not devoid of energy. Water reacting with iron-bearing minerals in serpentinization reactions releases hydrogen, a usable energy source. Radioactive decay in the Martian crust, though Mars is less radioactive than Earth, still generates a small but continuous flux of energy. And where water contacts certain rock types, redox chemistry between oxidized and reduced minerals provides the electron donors and acceptors that chemolithotrophs, microbes that live on rock chemistry rather than sunlight used to power their metabolism. On Earth, precisely these environments support life. Mines drilled to depths of several kilometers have found microbial communities living in cracks and pores, surviving on the chemistry of the rock around them, completely isolated from the surface and from sunlight for millions of years. Deep ocean crustal drilling has recovered living organisms from basalt hundreds of meters below the ocean floor. If life is genuinely widespread in the deep subsurface of Earth, and the evidence strongly suggests that it is, the question for Mars is not whether the physics and chemistry of the deep subsurface could support life, but whether life ever got established in those environments during the Noachian, and whether it has persisted there through 3 billion years of subsequent cold. The significance of that question for everything else we think we understand about the universe is difficult to overstate. If life began on Mars independently of Earth, it means that the emergence of living chemistry from non-living chemistry is not a singular cosmic accident. It means life arises wherever the conditions permit, on planets around other stars, in the subsurface oceans of icy moons in environments we haven't yet imagined. The universe would be inhabited, crowded at the microbial level, even if complex and intelligent life remains rare. There is another possibility that the data raises but cannot yet confirm: panspermia. Mars and Earth have been exchanging material since the solar system formed. Large impacts on Mars eject rock into interplanetary space at velocities high enough to escape Martian gravity. Some of those rocks, following orbits that eventually cross Earth's path, arrive here. Hundreds of Martian meteorites have been identified on Earth. Rocks whose chemical composition matches the Martian atmosphere and crust as characterized by our spacecraft. The most famous is ALH 84001, which we examined earlier, but it is one of a larger family of Martian rocks that have been collected from Antarctic ice sheets and desert pavements, each one a messenger carrying the chemical fingerprint of another world. Earth rocks reach Mars too via the same mechanism. If life existed on early Mars, and if microbial life can survive the journey, dormant inside a rock, shielded from radiation by centimeters of surrounding stone, metabolically inactive during millennia of transit, then it is not impossible that life on Earth and life on Mars share a common origin. We might be Martians. Microbes carried from Mars to Earth during the first billion years of solar system history, when impacts were frequent and interplanetary transfer more probable, could have seeded Earth with the precursors of everything that came after. Conversely, if Martian life shares ancestry with Earth life, finding it would not answer the deepest question: whether life arose independently on two planets or arose once and spread. To distinguish between those two scenarios, scientists would need to know whether Martian life uses the same genetic code, the same amino acid chirality, the same fundamental biochemical machinery as Earth life. Life with different chemistry would be definitively independent. Life with the same chemistry might be independent, evolution converging on the same solutions, or might be related. The resolution would require molecular biology performed on Martian samples in Earth laboratories, sophisticated enough to read whatever information the samples carry. The significance of finding life on Mars or finding nothing extends even beyond the question of biology. It bears on one of the deepest puzzles in modern science: why the universe appears silent. The physicist Enrico Fermi famously asked in 1950 if the galaxy contains billions of stars, many of them billions of years older than the Sun, and if life arises readily wherever conditions permit, then where is everyone? The galaxy is old enough that a civilization expanding at even a tiny fraction of the speed of light could have colonized every star system within a few 100 million years. Yet we detect nothing. The radio sky is silent. No artifact, no signal, no unmistakable sign of anyone. Mars data bears directly on this problem. If Mars was habitable for hundreds of millions of years and life never arose there, it suggests that the origin of life is genuinely rare, a cosmic accident improbable enough that it may have happened only once in the visible universe. In a universe where life barely gets started even on hospitable planets, the silence of the cosmos is expected and explicable. In a universe where life arises easily wherever conditions allow, as Martian life would suggest, the silence becomes more mysterious and troubling. Something must prevent civilizations from expanding, communicating, or surviving long enough to be detectable. The great filter, as some theorists call it, might lie behind us in the improbability of life's origin, or it might lie ahead in some catastrophic barrier that no civilization has yet overcome. Mars may help us determine which. Neither answer is small. The Martian sample return mission, those sealed titanium tubes waiting in the ancient delta of Jezero crater, could return the most consequential laboratory samples in scientific history, or they could confirm the Viking verdict and find nothing biological. Either way, the knowing matters more than the not knowing. 45 years after Viking's ambiguous biology results, we are still trying to answer the question those landers first posed. The patience required is geological. The stakes are everything. Every image transmitted from the surface of Mars, every rock photographed by a rover, every sunset recorded by a lander's camera, every measurement of soil chemistry and atmospheric composition is a step in an inquiry that began when the first human being looked at that red star and wondered what it was. The planet sat through 4 billion years of solar wind, meteorite bombardment, and geological transformation before we invented the mathematics to compute an orbit, the chemistry to build a rocket, the electronics to transmit a photograph across 200 million kilometers. We are very new to this. The planet is very old. And the distance between us in the scale of what the cosmos contains is almost nothing at all. The day will come when human beings stand on the surface of Mars and look up at Earth, a pale blue dot in a dark sky, just a point of cold light carrying everything the species has ever known. From that vantage point, looking back across the distance that robotic emissaries have been crossing for 60 years, the journey will seem both impossible and inevitable. Impossible because of the distance, the radiation, the cold, the years of transit, the cost of every kilogram lifted from Earth's deep gravity well. Inevitable, because curiosity is among the most durable of human instincts, and because some questions, once you have seen enough of the answer to understand the stakes, cannot be left unanswered forever. Mars is the next world, not the last one, not the most distant or the most strange or the most hostile of the worlds we will one day visit. But it is the next one, the one that has been watching us since before we understood what we were watching, the one whose secrets are within reach of the technology this generation will build, the one that carries whatever answer exists to the question of whether we are alone. That question has been asking itself for as long as there have been minds capable of asking it. Mars has been waiting patiently for someone to come and listen.